Likewise, the development of quantum computers could be even more significant in history than what we are witnessing, the beginning of yet another major shift in human history. The beginning of a groundbreaking change. A gloomy cloud swept over the scientific community when an advanced quantum computing system, once praised as a game changer, was suddenly disabled due to critical emergency concerns. The extinction of the mystery. Michio Kaku, a theoretical physicist of international fame, made an awe-inspiring and startling revelation. The interview unveiled troubling details concerning the course of quantum computing. He went on to include shocking information involving intelligence from other planets and insights into artificial consciousness, insights that impacted the global scientific landscape like a crashing sound. What brought about the instantaneous shutdown of this powerful quantum machine? Michio Kaku had jaw-dropping information, and this time he brought it to the attention of the general public. Keep an eye on us as we investigate this emotional moment when Kaku was clearly shaken to the core, even moved to tears. A quantum computing system came to a sudden halt, silencing the music of the 21st century. In this century, a series of significant innovations has altered the very foundation of our civilization. Industries were reimagined, granting capabilities to humanity once confined to science fiction. This transformation resulted from the startling rise of artificial insight into the enigmatic world of quantum computation. This era has produced one groundbreaking breakthrough after another. One of these pioneering developments stands out as especially promising and transformative. Field once ignored as a speculative theory by a few ambitious quantum scientists. Today, computing has developed into an advanced technology capable of accomplishing tasks once deemed impossible. The seeds of this transformation were initially planted in the 1900s, when quantum theory emerged as an innovative idea in physics, deciphering the mysterious behavior of atomic and subatomic particles. This laid the foundation for the field of quantum mechanics, which ultimately led to the theoretical underpinnings of quantum computing. However, the idea of using quantum mechanics for computation did not make significant progress until 1980, when the visionary scientist Paul Benioff proposed a daring new approach. Based on quantum principles, he suggested that quantum systems, utilizing phenomena like superposition and entanglement, could revolutionize computation. Shortly after, physicist Richard Feynman expanded on this idea. In 1982, he presented a compelling vision: computers built exclusively on quantum mechanical principles. According to Feynman, these machines wouldn't merely enhance existing technologies, they could solve computational problems so complex that traditional computers would become obsolete. Although revolutionary at the time, Feynman's idea remained largely theoretical. It wasn't until the 1990s that observable progress began to materialize. Brilliant minds across the world pushed toward Feynman's vision. Legendary mathematicians like Peter Shor contributed significantly to the development of this quantum saga. A turning point came in 1994, when Shor introduced a quantum algorithm so disruptive it sent shockwaves through the scientific community. His elegant method demonstrated that quantum computers could decipher complex cryptographic systems and perform computations that classical machines couldn't match. Shor's work sparked renewed interest in building functional quantum devices. Nearly a decade later, practical quantum computers began to emerge, though still basic. These machines represented the first visible steps toward a technological revolution. One of the early pioneers, Isaac Chung, collaborated with Neil Gershenfeld at MIT and Mark Cubanek at the University of California in 1998 to create a fundamental 2-qubit quantum computer. This prototype, constructed at Los Alamos National Lab, demonstrated the core principles of quantum computation in action. Although limited in practical application, the initial model was a foundational step. It used only 2 qubits quantum bits, the fundamental units for storing and processing quantum information. The computational power of a quantum system grows exponentially with the number of qubits. A 2-qubit device was almost insignificant compared to the enormous potential of a 10,000 qubit supercomputer. However, the marvel of quantum computing lies not just in qubit quantity, but in the unique nature of individual qubits. Unlike classical bits, which can be either a 0 or 1, qubits possess the extraordinary ability to exist in multiple states simultaneously, property known as superposition. To illustrate, a classical bit is either 0 or 1 with no overlap. A qubit, however, can represent both 0 and 1 at the same time. This remarkable attribute enables qubits to adapt to different conditions in real time, fundamentally changing how data is represented and processed. Superposition is one of the greatest gifts of the quantum world, and it has ignited great excitement among computer scientists and physicists alike. Quantum computers can perform calculations and solve problems at speeds and scales that traditional computing simply can't match. A crucial component of a quantum computer is its gate system. These gates operate similarly to logic gates in classical computers but manipulate qubit states in complex ways, allowing for the execution of sophisticated quantum algorithms. The elegance and depth of quantum gate operations are enough to even experienced scientists. In 2001, yet another milestone was reached. IBM researchers successfully used nuclear magnetic resonance (NMR) techniques to control the states of qubits in advancement that allowed precise manipulation of quantum systems. This was a thrilling moment for the field and opened new doors. For the future of computing, the first flawless application of Shor's algorithm marked a turning point. It didn't just demonstrate theoretical viability, it shocked the scientific community and sparked a surge of motivation to further explore quantum technology. Riding the momentum, quantum systems began to evolve rapidly. The number of qubits in advanced machines started increasing exponentially, allowing for calculations that traditional computers couldn't handle. In 2010, a breakthrough came from the University of Science and Technology of China: quantum teleportation, a phenomenon long considered science fiction. Quantum teleportation involved transferring the state of a quantum particle from one place to another without the particle physically moving through spacetime. The researchers transported quantum information over a distance of 10 meters, a milestone suggesting that quantum communication networks could someday replace our current internet. Just 3 years later, 2013, a groundbreaking collaboration was launched. In an unprecedented partnership, NASA and Google joined forces to build the D-Wave, an extraordinary quantum computer housed at NASA's Ames Research Center, designed to explore alien planets and revolutionize data processing. The D-Wave's potential applications seemed limitless. At the time, Google engineering director Hartmut Neven spoke about the promise of D-Wave 2. He noted that quantum computing could solve the most complex problems in science, especially in machine learning. Machine learning requires precise models of reality to predict outcomes, whether for medical breakthroughs, environmental policy, or enhancing search engine algorithms. Neven believed quantum systems could be the missing link in building such models. Indeed, D-Wave 2 delivered staggering performance, processing some tasks up to 10,000 times faster than conventional computers. It excelled in complex machine learning, challenges that rendered classical systems ineffective. Experts believed its capabilities were just scratching the surface. NASA's departments and the broader scientific community began speculating whether such a system might even help detect extraterrestrial life. A new theory among cosmologists proposed that black holes might function as natural quantum computers, perhaps used by intelligent alien civilizations. This theory helped explain why no solid evidence of alien life has been found. Perhaps their technologies are so advanced that they're invisible to us. If humans could build quantum computers mimicking black holes, discovering alien civilizations might become possible. The D-Wave machine was seen by many as a first step in that direction. Sadly, this dream was cut short. The government shut down the D-Wave project, disappointment driven by serious concerns within both scientific and intelligence communities. Chief among them, the fear that quantum computers could be used for cyberactics or other malicious purposes. Quantum machines can bypass modern encryption systems. Current cryptographic methods rely on complex equations that traditional computers can't solve within a feasible time frame. But a quantum computer could break them in seconds, turning decades of security into vulnerability. This terrifying possibility raised urgent red flags. If such power fell into the wrong hands, the consequences could be catastrophic. NASA halted its use of quantum systems, including the D-Wave, but Google pressed on. In 2019, it achieved a historic breakthrough: quantum supremacy. This momentous event was powered by Sycamore quantum processor. Quantum supremacy refers to the point when a quantum computer solves a problem no classical computer can solve in any reasonable time frame. Sycamore's processor did just that. Such a problem would have necessitated the most powerful supercomputers in the world millions of years to figure out. Yet quantum computers could compute it in a matter of seconds. The repercussions were stupendous, turning heads in the technological and scientific communities as well as the public at large. Awareness of the capabilities of quantum computing surged then. In 2020, the technology giant IBM made a significant comeback to the spotlight with the release of its IBM Q system. First of its kind, a worldwide developed integrated quantum computer designed specifically for use in businesses. In contrast to all prior quantum machines which were restricted to academic study or government use, the IBM Q was designed to be available to private businesses and individuals as well. The widespread adoption of quantum technology marked the beginning of a new era, one in which startups and enterprises could experiment on their own terms with quantum systems. Additionally, quantum computers meant that NASA and other scientific organizations could finally return to their investigations of alien intelligence, equipped with tools capable of surpassing the restrictions of conventional technology that limit human existence. The possibility of life on other planets remains an extremely likely scenario. In the end, quantum computing may provide the key to solving one of astronomy's greatest bafflements, the Fermi paradox. The paradox addresses the contradiction between the high statistical probability of civilizations from other planets or galaxies and the utter lack of observable evidence of such entities. If, in theory, there were indeed advanced forms of life out there, especially ones that had developed spacefaring capabilities, why haven't they left behind visible evidence, signals, or artifacts? What if we are simply incapable of detecting them? The issue might not be the absence of alien civilizations, but our own limitations. What if intelligent extraterrestrial life exists at a technological level completely undetectable by today's instruments? Next-generation quantum machines may possess the power almost unimaginable to begin uncovering the truth. This shocking idea is currently gaining significant traction among influential physicists and astronomers. Renowned scientists like Dr. Michio Kaku have joined the conversation, contributing to the growing belief that quantum computing could be the missing component in our quest to find intelligent life beyond Earth. With advancements in cosmic detection, scientists are expanding beyond traditional methods. Extraordinary approaches are being explored, ranging from the detection of high-energy particles to experiments in quantum-based communication networks. In an engaging discussion, Michio Kaku, a theoretical physicist, proposed a shocking theory. The universe could be threaded with a hidden superhighway between stars, designed by civilizations from other worlds. This covert system, according to Kaku, could allow an infinite number of alien entities to traverse the expanse of space undetected. This possibility could be the missing piece in our long-standing mystery the silence of the universe despite its age and vastness. Yet we may still lack the technological thresholds necessary to explore such a concept thoroughly for decades. The scientific community has focused on monitoring radio waves from distant stars, clinging to the hope that alien civilizations might announce their existence. But this narrow approach may be drastically reducing our chances of identifying extraterrestrial life. Perhaps once the enormous processing capabilities of quantum computers are fully unlocked, it's the means to find and investigate this elusive interstellar network to which Kaku alludes will finally be ours. Quantum computing remains today an emerging force praised for completing mind-bending tasks like high-fidelity deep learning simulations, significant optimization improvements, and solutions to problems once deemed unsolvable. But the full promise of quantum computing remains out of reach until physicists develop a more solid understanding of quantum bits, or qubits, the fundamental unit of quantum information. Without this mastery, we may never fully witness the remarkable capabilities of these machines. One of the most captivating aspects of quantum computing is a phenomenon known as quantum entanglement. Situation where particles become interconnected to the point that the state of one instantly impacts the other, regardless of distance, whether they are in adjacent labs or across galaxies. This enigmatic interdependence means that qubits can influence each other even if separated by light years, what Einstein famously called spooky action at a distance. This kind of connectivity enables qubits to process massive amounts of data collectively and simultaneously. It gives quantum computers a seemingly supernatural quality, like the ability to decipher encrypted systems or solve extremely difficult mathematical puzzles in mere seconds. Some technologists and industry leaders speculate that in just 5 years, quantum computing could append the entire encryption paradigm we use today. You might now be asking yourself, should we be worried about this? Is there not a real risk that quantum computers might fall into the wrong hands, leading to an increase in cyber attacks or catastrophic breaches? Fortunately, technology is evolving to counter these threats. Digital security has already taken steps forward. Researchers and cryptographers are hard at work creating quantum-resistant encryption methods, ultra-secure algorithms capable of defending against quantum hacking strategies. These new codes act as digital fortresses engineered to withstand even the most technically advanced cyber attacks. The goal of these cryptographic defenses is to go far beyond current encryption standards, ensuring the protection of confidential information and preserving the integrity of vital infrastructure well into the age of quantum physics. Yet the application of quantum computing extends far beyond cybersecurity. Its ability to recreate atoms and simulate complex molecules holds cutting-edge potential in industries such as pharmaceuticals, AI development, and materials science. Imagine designing sophisticated medications by modeling how they behave at the atomic level before conducting a single test in the lab. In the financial sector, quantum machines are being trained to analyze massive data sets, detect hidden vulnerabilities in complex systems, and optimize investment strategies with unprecedented precision. These machines can replicate real-time financial ecosystems, predict market behavior, and help institutions prepare for every possible economic scenarios, something classical supercomputers can't achieve. Despite all this promise, the path to quantum dominance remains obstructed by numerous challenges: technical incompatibilities, high costs, and a shortage of professionals with quantum expertise. Building a working quantum computer is nothing like building a better laptop. It requires a fundamental rethinking of hardware, technology, and every step of the programming process. It demands long-term planning, precise calculations, and extensive experimentation. Till these challenges are resolved, the full potential of quantum computing will remain just out of reach. In this context, Michio Kaku envisions a future one defined by a historic breakthrough, capable of altering human understanding itself. According to Kaku, Once we fully harness the synergy between artificial intelligence and quantum computation, we will enter a new epoch of scientific progress. A point will be reached where machines begin making discoveries beyond human comprehension, accelerating progress at a pace never before imagined. Some futurists believe this revolutionary pairing might not just propel us forward, could reshape society entirely. Alongside quantum computing, another potent force looms: large artificial intelligence. With the right input, AI could evolve into something significantly stronger than any system we've ever built. Many thought leaders believe that quantum computing and AI together will usher in a new digital age, according to Kaku. The moment these two titans, software powered by revolutionary technology and physics grounded in quantum mechanics, converge, we may witness the birth of machines with capabilities beyond comprehension. Although AI is already highly skilled at absorbing and replicating massive data sets, it still struggles to distinguish fact from fiction. Misinformation can enter AI models, and they can be easily manipulated to produce erroneous or biased content. But incorporating quantum computing into this process could change the game entirely by leveraging quantum entanglement, superposition, and probabilistic inference. AI could filter data with extreme precision, becoming a tool that not only understands content but verifies it at its core. These enhanced computational abilities would dramatically improve accuracy and ensure the integrity of digital information at a previously unreachable level. Imagine AI systems powered by quantum technology that not only respond to questions with astonishing speed and precision, but also demonstrate analytical foresights, predicting human needs, or even attempting to foresee future events. These wouldn't just be machines, they would be interpreters and predictors, actively engaging with data in real time. This vision has already stirred excitement in the scientific community. Researchers and engineers around the world are eagerly anticipating the first fusion of AI and quantum technology. To them, this is not just another step forward, it is the next great leap in human innovation. The convergence of these two realms could lead to breakthroughs across every conceivable discipline, from medicine and economics to environmental science and space exploration. However, with all